Hello everyone. Today we start chapter 5 on computer system architecture course. The title of this chapter is Basic Computer Organization and Design. The topics covered in this chapter are instruction codes, computer registers, computer instructions, timing and control, instruction cycle, memory reference instructions, input, output and interrupt, complete computer description, design of basic computer, design of accumulator logic. Morris Mann proposed in this book a basic computer, which is very small compared to commercial computers. And it has the advantage of being simple enough so we can demonstrate the design process without too many complications. The organization of the computer is defined by its internal registers, the timing and control structure, and the set of instructions that it uses. The internal organization of a digital system is defined by the sequence of micro-operations it performs on data stored in its registers. The general-purpose digital computer is capable of executing various micro-operations and, in addition, can be instructed as to what specific sequence of operations it must perform. The user of a computer can control the process by means of a program. A program is a set of instructions that specify the operations, operands, and the sequence by which processing has to occur. A computer instruction is a binary code that specifies a sequence of micro-operations for the computer. Instruction codes together with data are stored in memory, and this is according to the stored program concept developed by John von Neumann. The computer reads each instruction from memory and places it in a control register. The control then interprets the binary code of the instruction and proceeds to execute it by issuing a sequence of micro operations. Every computer has its own unique instruction set. The ability to store and execute instruction, the stored program concept, is the most important property of a general purpose computer. An instruction code is a group of bits that instructs the computer to perform a specific operation. It's usually divided into two parts, each having its own particular interpretation. The first part is called the operation code, and the second part is called the address part. The operation code of an instruction is a group of bits that defines such operations as add, subtract, multiply, shift, and complement. The number of bits required for the operation code of an instruction depends on the total number of operations available in the computer. For example, if we have 64 operations, then we need 6 bits for encoding each operation. In this case, the size of the operation code field should be at least 6 bits. In general, if the size of the operation code field is n bits, then we can encode 2 to the power n different operations. Suppose, for example, that the bits 110001 are assigned for the add operation. In this case, when the operation code is decoded in the control unit, the computer issues control signals to read an operand from memory and then adds the contents of the location to a processor register. Usually, the basic register is called accumulator. For every operation code, the control issues a sequence of macro operations needed for the hardware implementation of the specified operation. For this reason, an operation code is sometimes called a macro operation because it specifies a set of macro operations. Again, the operation code part of an instruction specifies the operation to be performed: add, subtract, multiply. This operation must be performed on some data stored in processor registers or in memory. An instruction code must therefore specify not only the operation, but also the registers or the memory words where the operands are to be found, as well as the register or memory location where the result is to be stored. And this is the function of the second part of the instruction, which is the address field. Memory locations can be specified in instruction codes by their address. In the basic computer, we have 4096 locations, so we need at least 12 bits to address each location. Processor registers can be specified by assigning to the instruction another binary code of k bits that specifies one of 2 to the power k registers. Or if we have capital N registers, we need log n bits to address each register. There are many variations for arranging the binary code of instructions, and each computer has its own particular instruction code format. Instruction code formats are conceived by computer designers who specify the architecture of the computer. Computers that have a single processor register usually assign to it the name accumulator and label it AC. The operation is performed with the memory operand and the contents of the accumulator. If an operation and instruction code does not need an operand from memory, the rest of the bits in the instruction can be used for other purposes. So in the instruction, we have here the operation code. In general, address of operand or operand. So in the case if the instruction does not need an operand from memory, this part can be used for other purposes. For example, to perform different macro operations on registers, such as increment, clear, decrement, etc. It's sometimes convenient to use the address bits of an instruction code not as an address, but as the actual operand. In this case, the addressing mode is called immediate addressing mode. In the instruction, we have the operation code and the operand itself. For example, the instruction add 15 adds the value 15 to the contents of the accumulator. In this instruction, the operand is directly included in the instruction. So this type of addressing is called immediate. If the address field contains the address of the operand in memory, then we have a direct addressing mode. And if it contains address of address, then the addressing mode is called indirect addressing mode. Usually one bit in the instruction called the address mode bit I is used to distinguish between the direct and indirect addressing modes. In this case, the instruction format is as follows. We have the I bit, the operation code, and the address of operand. If I is 0, we have direct addressing mode, and if I is 1, the addressing mode is indirect. I will demonstrate the difference between direct and indirect addressing through example. Again, here is the instruction format. We have here the I bit, operation code, and the address field. First, indirect addressing, this bit is 0. Suppose that we have a program stored in memory with one instruction here 0 and the operation code for the add And in the address field, we have the value, for example, 300. And the contents of memory location 300 is, for example, 23A1 in hexadecimal. After reading this instruction, 0, add 300. Since the mode bit is 0, then we have direct addressing. The operation code is add. Then we have to read the operand stored at location 300, which is 23A1, and add its contents to the contents of the accumulator. Suppose that the contents of the accumulator is 1, 2, 1B, again in hexadecimal. The result of addition is C, B, 5, 3. And this will be the new contents of the accumulator. Again, in direct addressing, in the address field, we have the address of memory location where the operand is stored. Here, the effective address of the operand is 300. However, in indirect addressing, again, if we have in the memory one instruction with the mode bit 1 and add, and here we have 400. And suppose that the contents of the location 400 is 1500 in hexadecimal, and the contents of location 1500 is 1340. First, the instruction is read from memory and decoded in the control unit. Here we have 1 bit indicating that we have indirect addressing mode and add operation. Now this value is not the address of the operand. It's the address of memory location where the address of operand is stored. In this case, we have to access this location, retrieve its contents, and use it as an address. Now the contents of location 1500 is 1340. And this is the actual operand that should be added to the contents of the accumulator. Suppose in the accumulator we have the hexadecimal value A45B. Since the operation is add, then we'll have here B97B. And this value will be stored in the accumulator, replacing its old contents. As you see, in direct addressing mode, we have in the instruction the address of the operand, but in indirect addressing mode, we have in the instruction the address of memory location that stores the address of the operand. Here, the effective address is 1500. The indirect address instruction needs 2 references to memory to fetch an operand. So it's slower than direct addressing, but it has some applications. This address can be considered as a pointer, and in some general purpose computers, it can be stored in one of the CPU registers. Before leaving this screen, in direct addressing, after fetching the instruction, we have to access memory one time to read the operand. And in indirect addressing, after fetching the instruction, we have to access memory 2 times. The first time to fetch the address of the operand, and the second time to read the operand itself. Next, computer registers. Computer instructions are normally stored in consecutive memory locations and are executed sequentially, one at a time. The control reads an instruction from a specific address in memory and executes it. It then continues by reading the next instruction in sequence and executes it, and so on. The instruction cycle consists of three phases: read, decode, execute, and we will come to that in more detail later. This type of instruction sequencing needs a counter to calculate the address of the next instruction after execution of the current instruction is completed. And this counter is called program counter. The program counter holds the address of the next instruction to be executed. Suppose that we have the memory with the program stored in it. The memory location addressed by the program counter is read or fetch, decoded in the CPU, and then execute. The contents of the program counter is updated by incrementing it by 1, or in some computers by the size of the instruction. For example, if the instruction is 2 bytes, then we have to increase the contents of the program counter by 2. The next instruction is read or fetched, again decode, execute, and each time the address of the program counter is updated to hold the address of the next instruction. This scenario is good if we invent a transfer of control instructions where we have to jump to another area in memory. In this case, the address of the new location is stored in the instruction, and the execution of the instruction will store this value into the program counter. So the program counter now can access the new specified location. We will demonstrate that in the next sections. So the program counter is a special CPU register used to store or hold the address of the next instruction to be executed. In the basic computer, we have 4096 locations. So we need 12 bits to address each location. So the dimension of the program counter is 12 bits, 0 to 11, program counter. Really here another register is used to hold the address of the operand, and this register is called the address register. And again, its size is 12 in the basic computer. The difference between the program counter and the address register is that the program counter is used to hold the address of the next instruction to be executed, while the address register is used to hold the address of the operand to be fetched from memory. It's also necessary to provide a register in the control unit for storing the instruction code after it's read from memory. The computer needs processor registers for manipulating data on a register for holding a memory address. In the basic computer, the memory unit has a capacity of 4K locations, and each location contains 16 bits. According to the stored program concept, both instructions and data are stored in memory. So the instruction size is 16 bits, and we need 12 bits from these 16 in the address field, address part or field in the instruction. We have remaining 4 bits for the operation code, and 1 bit from these 4 is for the mode bit, direct, indirect addressing mode. So we have only 3 bits remaining here. for the operation code. After reading the instruction from memory, we place it in a register called instruction register, and the size of this register is 16 bits. And there is another register used to hold the operand. The data register holds the operand read from memory. The temporary register is used for holding temporary data during the processing. This is the map for basic computer registers and memory. We have 4 kilobyte of locations, 4096 locations, each of size 16 bits. This means that the address of data register, accumulator, temporary register, and instruction register should be 16. And the size of the program counter and the address register is 12 bits. Since we need 12 bits to address any of these locations. There are two registers, the input register and the output register of size 1 byte each. The input register receives an 8-bit character from an input device, and the output register holds an 8-bit character for an output device. A quick summary: both instructions, program, and data are stored in memory. A program counter is used to hold the address of the next instruction. So we read the instruction from memory and store it in the instruction register. After that, the contents of the program counter can be updated to hold the address of the next instruction. The instruction is decoded and then executed. If we need an operand from memory, then we use the address register to hold the address of that operand. Data register is used to hold the operand read from memory. Accumulator is a general purpose register where several arithmetic and logic operations can be performed, and it is considered as the CPU basic register. Input register is used to receive a character from the input device and later transfer it to the accumulator. Output register is used to hold the character received from the accumulator in order to transfer it to the output device. This is a list of registers for the basic computer. The size of data register is 16 bits and it holds memory operand. Address register holds address for memory and usually the address of the operand, and its size is 12 bits, the same as the size of the program counter, which is used to hold the address of the next instruction to be executed. The size of the accumulator and the data register and the instruction register and the temporary register is 16 bits, and it's the same as the size of any memory location. Input and output registers hold the input or output character, and they have the size of 1 byte. These are the registers used in the basic computer in addition to the memory of size 4 kilo locations, which is 4096 locations. I will stop here today. In the next video, we'll continue with the bus system. For today, that's all. Thank you.